Hello, AP Chemistry students. In this video, we're going to cover notes 6 and 7 in the Unit 3 notes packet. And these topics are not huge topics in Unit 3, but they are still things that could show up on the test or the AP test and are really kind of going to complete our understanding of gases and their behaviors. So one of the things that we've discussed throughout the unit is the ideal gas law. And if we think about the word ideal, this means that all the math involved in the gas law formulas that we've used so far talk about gases as behaving all the different postulates of kinetic molecular theory. However, no gas that exists in nature is truly 100% ideal. Every single gas will deviate from the math in the ideal gas law, but most of the time the deviations are so small that unless you went out 10 decimal places, would you actually see a difference in the math? And for example, even chemists at NASA will use the ideal gas law instead of some of these other ideas that we're going to talk about today, but they're still conceptually something that is important to understand. So one of the first things is below, here is what I call the real gas law. This is called the van der Waals equation, and we can see kind of PV equals nRT here. And so there's some deviations as far as pressure and volume. The first thing is that the pressure could be mathematically solved for as something slightly different if we actually take into account that there are attractive forces between gas particles. Although gases, we say, have very, very low intermolecular forces, they don't have zero intermolecular forces. And so this A term takes into account and measures the attraction between particles for a particular gas. One of the other postulates of kinetic molecular theory was that the actual gas particles, the space that the actual particles occupy is negligible. And while this is a true statement, the math behind PV equals nRT assumes that the volume of the container is equal to the volume that the gas occupies. And while this is pretty much true, if you think about it, if you think of all the students in the classroom right now, if we imagine that, student A, let's just call them Johnny. Johnny can occupy all kinds of space in the classroom. However, where you're located, Johnny can't simultaneously occupy that space. So far with our gas laws, we've assumed that that's no longer the case and that gas particles occupy no volume, but instead they do occupy some volume, and so this term B takes this into account. The good news is that we are never going to actually solve this. So this is just more for your information and to give us some context on the rest of these notes that we're going to cover. So gases behave ideally at high temperature and low pressure. You need to know this, okay? We're going to talk about why. If you are familiar with the NBA, I've always used kind of the Denver Nuggets to help us understand this. The Denver Nuggets are at a high altitude. Denver is commonly referred to as the Mile High City. So you can think high altitude. And if you've ever been on a plane, you should know that as you go up into the atmosphere, whether you're a mile up or many miles up, is that the atmosphere becomes very, very thin until eventually you reach outer space. And so how I always remembered this is Denver has a high altitude. And as a result, it has low pressure. So if we can remember that Denver has low pressure, then maybe we can kind of try to remember that the temperature has to be opposite, so it has a high temperature. Because gas molecules actually do have volume, and they do take up space, and they have attractions to each other, we can understand that at low that's not the right button. We can understand that at low temperatures, gas particles will move slower, and they'll actually condense closer to each other. And particles that are close to each other will have greater attraction. Additionally, gases at high pressures, gases are going to be forced closer together, and therefore their attractive forces will be larger. These attractive forces will actually lessen the force at which gas molecules hit the walls of their container, because similar to the picture down here, what this is trying to say is that normally a gas particle, we would say, hits the wall of their container, bounce back, and has no attraction to its surrounding particles. However, what a real gas does is it gets a little bit slowed down as it hits the wall of the container because there is some attraction here. And so the particles don't hit the walls of their container. And so to make sure that the math is as correct as possible, we want gases that have low IMFs to be ideal. And so what that means is that gases with high intermolecular forces will deviate from ideal behavior. So gases with strong attractive forces will deviate, and what we expect as a result is a slightly lower pressure. So if we go back to the Denver Nuggets here, we said gases behave ideally at high temperatures. Here's why. At high temperatures, we've kind of talked about heat them up, speed them up. Well, if we heat up our gas particles, they will be able to overcome these attractive forces and they won't be slowed down as a result. Additionally, gases behave ideally at low pressures because at low pressures, our gas particles, they'll be at not as close together, and when particles are less, or when they're further apart from each other, they experience less attractive forces. So let's try some examples with this. Example number 1 says, would you expect helium or carbon dioxide to behave more like an ideal gas under the same conditions? So one of the things that we haven't talked about yet is intermolecular forces, and one of the ways that we can talk about intermolecular forces is about the total amount of electrons present in an atom or a molecule. And more electrons means more London dispersion forces, and you might not remember that right now, and that's okay. But London dispersion forces are simply just an attractive force. Helium has 4 electrons, carbon has 6, and oxygen has 8, so 16 for both oxygens. And then we add 6, so we get 22 electrons if my mental math is right there. So if we go back and we think more electrons is more LDFs, we've said gases with high IMFs will deviate from ideal conditions. So I think carbon dioxide is going to have more intermolecular forces or stronger forces of attractions. So what I would say is helium is likely to behave like an ideal gas since helium particles experience less attractive forces. CO2 particles have more electrons and will have greater, attractive forces, causing deviation from ideal behavior. Number 2 says the clouds of Jupiter have an average temperature of 140 Kelvin and a pressure of 16,000 psi. Mercury, the planet, has a surface temperature between 600 and 700 Kelvin and a pressure of 7.25 times 10 to the minus 14 psi. On which planet is the atmosphere more likely to obey the ideal gas law? Just so you know, the average pressure on Earth is 14.7 psi. So I want to think about what are ideal conditions, and I think back to the Denver Nuggets. Ideal conditions is, okay, Denver is the mile-high city, so it has high temperature. And as you go up in the atmosphere, we get low pressure. So I want to find which one has the higher temperature, and that would be Mercury. Additionally, Mercury has the lowest pressure. Therefore, its gas particles have the kinetic energy needed to overcome attractive forces. And there's very low pressure, so the particles are not that close together anyway. And so as a result, Mercury, the planet, will have or behave the most ideally. In number 3, this is like an example for your response question. It says a student is doing experiments with carbon dioxide gas, and originally the sample of gas in a rigid container at 299 Kelvin and 0.7 atmospheres. The student increases the temperature to 425 Kelvin. Describe the effect of raising the temperature on the motion of carbon dioxide molecules. So for A, I would say increasing the temperature causes the particles to move. We want to talk about the motion with greater kinetic energy and speed. The phrase heat 'em up, speed 'em up is a really good one to be thinking about right now. However, that's not exactly, if you only wrote that, that won't get you full points. Now on B, it says calculate the pressure. We've talked in class now about how if you heat 'em up, you speed 'em up, and we have kind of joked around with these F words that we want you to be thinking of. So force and frequency. Increasing the temperature will cause the particles to move more. They'll move with greater speed and kinetic energy, and our particles will hit the walls of the container with more force and with more frequency. And as a result, we should expect the pressure to go up. However, this is a condition where this is a situation where conditions are changed. Specifically, it looks like volume is not changed. It's a rigid container. It looks like temperature is changed, and we're asked to solve about how temperature or pressure will change. So pressure and temperature are on opposite sides of the gas equation, which means it's a direct relationship. When it's a direct relationship, we need to divide our variables. So we get P1 over T1 equals P2 over T2. And what we can do is we can plug in 299 Kelvin as our initial temperature. We can plug in 425 as our final temperature. And we are asked to solve for our new pressure, and the pressure was originally at 0.7 atms. I'm just going to simply cross multiply and then divide. So 0.7 times 425 divided by 299. And I get a new pressure of 0.99 atms. I think that's good. So we've kind of already previewed this, but in C, we are asked, in terms of kinetic molecular theory, this means talking about the particles. Briefly explain why the pressure of CO2 in the container changes as it is heated. As the container, or let's actually change this, as the gas is heated, the volume stays the same. I think it's important to mention that the volume stays the same, that it's a rigid container. Otherwise, if it was a flexible container, the pressure could possibly stay the same. As the gas is heated, the volume stays constant. The gas particles hit the walls of the container with more force and frequency, resulting in a larger measured pressure. And then D says the student measures the actual pressure in the container and observes that it is less than the pressure predicted by the ideal gas law. Explain this observation. So if a gas particle is going to deviate, this is because it experienced attractive forces that we did not take into account in our calculations. So my answer is not going to be super long here. I'm just going to simply say, since CO2's measured pressure deviates from the ideal gas law, CO2 particles must experience greater attraction, or actually I'm going to change that to greater attractive forces that cause CO2 particles to hit the walls of the container with less force and frequency. Okay, we're going to keep moving on to note 7. Note 7 hopefully isn't anything too weird. There's just one thing about gas equilibrium that we haven't quite talked about just yet. So last unit, we learned how to calculate equilibrium constant K, and specifically, we were dealing with Kc, in which the C stand for concentration. And so if we're dealing with gases, we almost never describe gases in terms of molarity, although you could. So we typically describe the concentration of gases with respect to their pressures. And so we can actually get a new K, and this is the only K that's slightly different, and it's called Kp. With Kp, we do not use brackets, and instead we use parentheses. Since brackets represent molarity, it would be inappropriate to use pressure with brackets. And so we simply get the same exact Kp expression, and all that I want to be able to do is be able to manipulate Kp. So for example, we have this reaction where we have 2 N2O plus 3 oxygens in an equilibrium system to produce 4 NO2. We are asked to solve for the expression, and we just say Kp. It's still equal to products over reactants. My products are NO2. Because everything's gases, and I'm dealing with Kp, it makes sense to say the pressure of NO2, I put it in parentheses, and I'd still put it to the 4th power. I'm going to now divide it by the pressure of N2O to the 2nd power multiplied by the pressure of diatomic oxygen to the 3rd power. On this next one, I'm still going to get Kp. This time, I want you to look at reaction A and compare it to reaction B. I hope you notice that all we did was we flipped reaction A. So I'm going to get the same thing, but I'm simply just going to get the reciprocal, where the pressure of N2O squared times the pressure of O2 cubed divided by the pressure of NO2 to the 4th power. If you remember from last unit, we would say if we just flipped a reaction, we'd just get K to the minus 1 power. Our K from before was 4. So we'd say 4 to the minus 1 power, which you can use a calculator, and you get 0.25. Now, if we go back to our original reaction and we compare it to C, I hope you see that we halved this. So our K is now just going to be to the 1/2 power, or the square root. Square root of 4 is just going to be 2. This time, we're going to get Kp, and actually, I'm going to be a little clever here. I'm going to copy my Kp from up here since the order of the reaction didn't change. And I'm just going to get different exponents. We had NO2 now to the 2nd power. We have N2O to the 1st power, which you wouldn't have to write. Then we have O2 to the 3/2 power, which you can definitely have fractional exponents. Okay, time for our very last one here. In number 2, it says calculate the value of the equilibrium constant for the following system given the data shown. And one thing I just saw instantly is I forgot to call COCl2 a gas. So if we want to solve for the value of the equilibrium constant, we're going to write our expression, which is Kp. Kp is equal to the pressure of COCl2 to the first power divided by the pressure of CO also to the first power and the pressure of Cl2 again to the first power. Everything just happens to be 1 here. And I'm just going to plug in what I know. So I'm going to plug in 0.1 atms divided by pressure of CO, which is 0.5, and divided by the pressure of Cl2, which is going to be 1 atm. Remember from Unit 2, K, whether it's Kp or Kc, will never have units. So even though I'm plugging in atms, my final answer is just going to be 0.2. Kp is less than 1. And so they ask, is this reactant or product favored? Because it's less than 1, I would call this reactant favored, which is a non-spawn reaction. Here, we could do something similar. This time, we actually have, I believe, our reaction from A here. So again, I'm going to copy it. I'm going to write my K expression like this. And we're going to, looks like, solve for P in O2. So it looks like I know Kp. Looks like it's 4. I'm going to plug in just x. And I'm going to make it x to the 4th power. I don't know what it is, but we'll solve for it. We have the pressure of N2O, which is 2.82. And our exponent says that it's going to be squared. Then we'll have the pressure of O2, and it will be to the first power. And we will cube it. Looking here, hopefully it makes sense that I can just simplify this and get rid of 1 cubed, because 1 cubed is going to stay 1. I'm now going to cross multiply. So I will take 2.82 squared, and I get 7.95, and now I will multiply that by 4, and I get 31.8096 equals x to the 4th. We will take the 4th root here of each side. If you don't like writing the 4th root, what you could also do, put it in parentheses and put it to the 1/4 power. That is the same thing as taking the 4th root. So in my calculator, I will have 31.8096, put it in parentheses, do a caret, and then do more parentheses, 1 divided by 4, and that should solve for our x just fine. And I get 2.37. And actually, because that is the pressure of NO2, I'm going to call this ATMs. That way it has appropriate units. Okay, the last thing is not on the test, but I'm going to keep going in the video. So if you're in year 2023 and you want to just stop the video now, that's great. But for me, I'm just going to finish these notes so that I have a video that covers them. Kp and Kc are not mathematically the same always. In fact, sometimes they are, sometimes they aren't. This equation used to be on the AP chemistry formula sheet, and who knows, maybe one day it'll show back up. But right now, in 2023, it is not. Kp is equal to Kc times RT to the delta N power, where delta N is equal to the change of gas products minus, let me reword that. Delta N is equal to the change of gas moles, specifically the moles of gas products minus the moles of gas reactants in the balanced chemical equation. R will be 0.08206 or 0.0821. And what would be good to know is that Kp is equal to Kc when you have equal gas moles on each side of the equation. That would essentially be an equation or a situation where the volume was changed and it asks which side of the reaction would the reaction shift, and you might say no shift because they have equal gas moles. So when I look at number 4, it looks like we have 1 gas mole on that side. And it looks like we have 2 gas moles on this side. Kc for this reaction is 0.0038, specifically at 250 degrees Celsius, which is only true, that's the only time that this K would be true. Degrees Celsius is wonderful stuff, but for us, we always want Kelvin, so I always like to pause. I'm going to call this 523 Kelvin. Our equation is Kp is equal to Kc, in parentheses, RT delta N. So our Kp is what we're solving for. We are given Kc to be 0.0038. Our R, and I'm going to use double parentheses here, is 0.08206 ATMs times liters divided by moles times Kelvin. Our temperature is 523 Kelvin, which is essentially just plug and chug. And now we need to figure out delta N. Delta N for us is going to be the moles of gas products minus the moles of gas reactants. So simply 2 minus 1. So this time it's a pretty easy number. We'll just put it to the first power. So when I plug all this into my calculator, I get 0.0038 and then 0.08206 and then 523. And my Kp is going to be equal to 0.163. Again, no units, but that is how you could convert between Kp and Kc.